I'm just thinking the camera. All right, we're live, and
all right.
there is Professor Jason Wright from Penn State University, who is going to tell us a little bit about some exciting stuff that's been happening recently with the most mysterious star in the universe, Tabby star. Maybe you can just lead us off, Jason, telling us what's exciting that's happening right now.
Sure. Well, it's kind of a weird coincidence that I'm here in the Breakthrough Listen Lab at UC Berkeley when all of this started happening. So, so Tabby star, as you may know, went through a lot of very strange dimming events. It got up to 22% dimmer during the Kepler mission. And since then, we've been eagerly awaiting another dip. And the reason that we've been waiting for that is that whatever's causing the star to get dimmer will leave a spectral fingerprint behind. So if it's a lot of dust between us and the star that's passing by, it should block more blue light than red light. If there's gas in that dust, that gas should absorb very specific wavelengths, and we should be able to see that. And so we've been eager to see one of these changes, one of these dips of the star, so that we can take some spectrum. So all week there have been some indications that something might be up, and yesterday we were on yellow alert. There was evidence from Fairborn Observatory in Arizona. Matt Mutersball let us know that they were seeing what looked like some dimming events, but nothing was significant enough for us to really hit the big red button and get everybody on red alert to start taking spectrum when this happens. One of the difficulties here is that most telescopes are scheduled weeks, months in advance, and so we can't just jump on a telescope and take a spectrum typically. And so we need to have a network of people around the world that are ready to jump on. And fortunately, Tabby star is not too faint. And so there are a lot of observers on telescopes around the world tonight, actually, that have graciously agreed to take some time out of their science to grab a spectrum for us. Anyway, so the punchline is that yesterday we were sort of on yellow alert waiting for data to come in to tell us if the dip was really happening. And sure enough, at about 4 a.m. This morning, I got a phone call from Tabby that that Fairborn Observatory in Arizona had confirmed that the star was 3% dimmer than it normally is. And that is enough that we are absolutely confident that this is no statistical fluke. We've now got it confirmed at multiple observatories, I think, that the star is indeed. So I guess I can show these data. Steve, do you want to put one of those up?
Sure. Which one do you want?
Okay, I don't know if this is coming through. Is there a way to zoom that in or project this in some way?
I can see if I can share this on.
Yeah.
Here, yeah.
All right. Well, Steve, we'll see if we can get the data shown so you can see exactly what this looks like. Because I don't think it's coming through on the webcam right now. The punchline is that it's been more or less stable in brightness for as long as we've been measuring it. There's some indications that maybe it's been slowly getting dimmer. That's the other strange thing that this star has been doing is it's been very slowly getting dimmer over many years. And we've been accumulating evidence that may be continuing to today. But just in the last 2 days, it got dramatically suddenly by about now, as of this morning at 4 a.m. Pacific, about 3% dimmer. And so we are officially on alert, and we are asking astronomers on telescopes, including amateurs with the American Association of Variable Star Observers, and all the way up to the spectroscopists on the Keck twin 10-meter telescopes tonight, to please take spectra of the star, multiband photometry of the star. We're going to do everything we can to understand how the dimming is different at different wavelengths, because as an astronomer will tell you, the key to understand what something's made of is to get a spectrum of it. And now we are able to get a transmission spectrum of whatever is blocking light. I think that's everything we've got right now. We're organizing lots of different telescopes. We have observers on the both Keck telescopes. We have an observer who's offered us some time on the MMT in Arizona. We have a team member that's trying to get infrared observations at the Large Molecular Telescope in Arizona. We're going to try to use the Minerva Telescope Array in Arizona. I'm going to trigger, as soon as I get around to it, some more spectra at the Hobby Eberly Telescope tonight. I know I'm missing a whole bunch of things that we're all trying to get done. But it's been kind of a crazy last 18 hours, and it'll be a really exciting weekend. So Steve, is this one up? Not quite yet, okay. Let's see, what else can I say before we get to questions? So Steve is frantically working here to try and show you the data so that you can see what the what we're talking about when we say that it's getting dimmer. Oh, so where am I exactly? I see a question on one of our channels here.
Yeah, this is up, actually.
This is up. Okay, great. So here is the this is the light curve from this is Fairborn Observatory. Matt Uterswasser has this plot recently, and it shows all the red points for most of this are just essentially the star being more or less the same brightness. The green points around 578060 to 57880 were the first hint something wonky might be going on. There was that cluster that was a little lower than usual, and so we started getting very interested. And then the blue points are what Matt has labeled event 2, and you can see that they are significantly lower. One of those points has very low error bars, so it's highly statistically significant. And so the fact that all of those went down, those are the observations that had us push the big red button, so to speak. And then we get the LCOGT data as well, which is the next, the next one over.
Oh, that's on here, so I gotta, sorry, load that up on
okay, and
computer.
there's one more that I'll show in just a bit.
Right, I'll just stop this for a second, and we're back on the video again now. This is some horrible URL that I'm gonna have to type in here, so keep talking for a second.
No problem. Do you want me to paste it into the, I can just paste it.
Maybe easier if I just do this.
Okay.
I don't know how I get that.
Let me see, maybe I can find some questions here.
And here comes Dr. Andrew Semien. Do you want to sit around this side, Andrew, and you can join the chat? You can be on the screen. Actually, I guess we can see.
And then overhearing the very exciting chat.
Okay, we're live now, so do you want to introduce yourself, Andrew?
Yes,
Some
I am
before, but...
Andrew Siemion here in the Berkeley SETI Research Center, Breakthrough Listen Lab, and it's Super Bowl Sunday.
That's right, it's the main event.
Everybody's been quiet since we're broadcasting here, but there's certainly a palpable tension.
That's right. So we have Green Bank. We're hoping that we'll be able to make some Green Bank up.
Yes. So
permission. I was explaining that telescopes don't schedule on this kind of short notice, and so a lot of this is begging and borrowing and asking, and a lot of people graciously offering their time to us.
Yeah, absolutely. I mean, I think that's kind of a really fun thing about moments like this is that you get these giant email threads with astronomers from all over the world, and especially in a situation like this.
And people you've never met.
Yeah. And
they're just like really wonderful about this.
So let's see, as far as Breakthrough Listen goes, we're confirmed on the automated planet finder. This is a 2.4 meter optical telescope with a very precise spectrograph. It's here in California at Lick Observatory. We'll have a 1 hour exposure on KIC 846-2852 this evening. That's confirmed. And we're working with our colleagues at Green Bank to get on that facility here in probably the next 12 hours or so.
Great.
So as Jason said, this involves some kind of informal swaps with other observers at the telescope, but we're hopeful we'll be able to get some time there as well. So it's
right.
it's very
so these would both, so the Green Bank observations, to be clear, would be with the Breakthrough Listen SETI radio backend.
That's right. Yeah, the Green Bank telescope is a 100-meter class radio telescope. It's one of the largest fully steerable radio telescopes in the world, if not the largest. It has a really fantastic surface accuracy. It allows it to observe at very, very high frequencies, up to about 100 gigahertz, 115 gigahertz or so. And I think essentially our plan will be, although this is very much in sort of discussion here this afternoon, is to observe at as many wavelengths as we can. Cool. So with as many receivers as we can observe. And of course, this is really an extension of the program that UPI, which was awarded time from the Time Allocation Committee for the telescopes. We already have 24 hours of data with Jason's program. But it's very exciting to actually get data when one of these dimming events is happening.
And since we're doing this, and people have been asking, we collected about 610 terabytes or 600 terabytes of data. And it turned out that the safest way to move that much data to Penn State, where we will do the analysis, was just over the internet. And we have the third run is supposed to complete its transfer to Penn State this weekend. And then the fourth run and final run will happen over the next couple of weeks. And one of the reasons I'm here actually is to get the software running at Penn State so that we can do the really thorough, careful analysis that we want to do with those data. We have a whole bunch of questions here, now I see. And it's, okay, go ahead. Oh yeah, why don't we see the LCOGT data while we're here? Great. So these are the data from the Luce Global Telescope network. These are data that we are able to take thanks to our Kickstarter backers who participated in the Where's the Flux Kickstarter. And we now have a year of time that Tabby manages on this telescope network. And so the tick marks on the bottom are in units of days. And you can see, just like with the Fairborn Observatory data, things are very constant until just the last couple of days. We saw this big dip that had us on yellow alert. And then last night, or early this morning, things were way down a full 2.5% from baseline, or 2%. This is a slightly different filter, so that's not necessarily inconsistent with the Fairborn data. And that's what's got us all so very excited. So yeah, it has been all over Twitter. My phone has just been going crazy.
Charles Choi had a question, the American, how soon might you be able to know something?
It's a good question. I guess it depends on what we see. You take data at the telescope, you have to reduce it. And so that means you have to take what the telescope gives you and turn it into some sort of spectrum that you can analyze and look at. Some of the observers on tonight will have automated pipelines. They can just turn the crank, and by tomorrow morning, we will have beautiful spectra that we can then inspect. Others will be changing their instruments into modes they don't normally use, and those data will take some more time to reduce because they'll have to tweak their pipeline to properly handle it. And then I guess it depends on what we see. If we see much stronger line, the other issue is whether we have data from that spectrograph before. If we take data with the same instrument in the same way, then it's very straightforward to look for tiny changes in the spectrum. But if the data we're taking with very different instruments, then you have to ask what differences are due to the fact that they're different instruments and what's due to the star itself. And that's a more involved analysis procedure. And so that'll take a lot longer. I don't know what we'll see. It could be we'll look at the data and throw up our hands and say we have no idea, this will take months to understand, or it could be something painfully obvious and we'll all slap our foreheads and say, oh, that's what it is. I don't think we're going to solve the puzzle this weekend, but it is possible that this weekend will be the weekend where we took the data that solved the puzzle. But we've, a lot of people here contributing a lot of data, and it's going to take a lot of time to sort through it all and figure out what we have, but it's all very exciting.
I think from the SETI standpoint, one thing to keep in mind is that our ability to discern some signal as being technological depends quite a lot on how strong the signal is. So if there's something as obvious as the dimming in the radio, we would know that immediately after taking these data. So we actually have a real-time analysis pipeline for breakthrough listen that we've just gotten working in the last several months, and we'll be deploying that pipeline on the observations with GVT this evening if we can get on the telescope. And so we would know very, very quickly if there was something associated with the dimming event also in the radio. So I think an exciting couple of days ahead of us.
That's right. People wanted to know if the dimming is a surprise. Yes, there was no real pattern predictability to the dimmings that Kepler saw. This is the first time we've seen a clear dip, or a clear dip in the star's brightness since the Kepler mission, and it's also the first one we've caught in real time. So we know it's going on right now, or at least it was going on strong at 4 a.m. this morning. Most of the dips in the Kepler data took something like 2 to 7 days, depending on how deep they were. So if this is a deep dip, this might be going on for a week. If it's a very shallow dip, it could be that tomorrow it's already on its way out. So we're thankful that we have at least a little bit of data from last night, and we're hopeful that that this will be a deep dip, and that tonight we'll get some really fantastic data.
And there's some evidence for, correct me if I'm wrong, Jason, some multiplicity in these sort of events. So there's a better probability that we'll see an additional dimming event.
They were highly clustered in the Kepler data. I mean, some of them were isolated, but in the final quarter that Kepler observed, I mean, it went on for like a month or something. Just lots and lots of dips.
So we could be at the beginning of a very
extraordinarily exciting. I could have a very busy month ahead of me, yes. I definitely have a busy month. There was some suggestion the two deepest dips in the Kepler data were almost exactly 2 years apart, but that might be significant. I didn't really put much stock in that, but it was something to go on. Anyway, that window passed just a couple months ago, so this is like 4.5 years or something, or 4.4 years after the deepest dip in Kepler, the second deepest dip. Let me see, what are some good questions people are asking?
So Charles Choi, I think, had a follow-up, which was, I think, just for you to explain specifically what the difference is between the spectral signature of artificial structure and the spectral signature of just a cloud of dust or something.
So, if it's dust, we expect, as I said, more dimming at shorter wavelengths. So we have the SWIFT telescope, which can make observations at ultraviolet wavelengths, although at less precision. And so if it's typical dust reddening, then 3% in the red, where these data we showed earlier were, would be more like a few percent, several percent out at the blue edge of where humans can see, and then even deeper in the ultraviolet. So the SWIFT telescope, unlike most telescopes, especially those in space like Hubble, can be retasked on the fly. It was designed to drop everything and look at a new source in a matter of seconds to catch gamma ray bursts. And so we're going to take advantage of that, not quite that level of interruption, but I'm told that we have data coming in today on that. So that's great. If there's dust, gas in the way, just about any astrophysical dust and gas should contain large amounts of sodium, hydrogen, calcium. And so we'll be looking at the strong spectral features of those elements to see if during this dimming event there is new absorption at those wavelengths, which would indicate that whatever's doing the absorbing has large amounts of those gases, which is sort of what you would expect. If we see a lot of lines from those gases, we can do diagnostics and determine how dense it is, what its temperature is, if that's what's going on. We have people observing at the Large Binocular Telescope in interferometry mode at 10 microns. That's useful because that's infrared flux, and that's the big missing, that's the missing piece that makes this so strange, is that if this material is circumstellar, like comets or a disk around a star, you expect the star to heat that stuff up. And so the lack of any emission in the infrared, this thermal heat coming off of this material, has always been the central mystery of Tabby star. The best explanation, the one that Tabby and her team put together when they first announced the system, is that it's due to stuff on very elliptical orbits, giant comets, essentially. And so if these dips are being caused by the passage of gigantic comets, then they should be very close to the star right now. They should be very hot. So we would love to get infrared monitoring of this star right now and see if that infrared excess has finally shown up. If that does show up, then that would strongly favor these circumstellar explanations and say that the material blocking the light is close to the star. And that would really, that might be the thing that happens very quickly if we have a strong measurement of infrared emission from last night or tonight. And then in terms of, yeah, what you would see with aliens, I don't know. I mean, the alien megastructure hypothesis would say that what's blocking the light is solid. It's not transmissive at all. And so the star should just get dimmer overall. So like a flock of starlings in front of the sun, you just blocked a bunch of light in certain places, and so the whole spectrum would get dimmer, and I guess you wouldn't see anything. Or if it was a really large structure and just part of the star, we would actually notice that as a change in the spectral line shapes.
Because perhaps some very sort of bizarre absorption features. Something.
Right. If we saw absorption from tritium or technetium or some artificial element and nothing natural, that would do it. But I want to emphasize that you know, the SETI is along for the ride on most of these observations. That whatever we see, we're gonna study, and it'll be interesting. And that I don't want to predict what, you know, what it might be if it were aliens. I think it's fair to say most of the people donating their time on the telescopes, you know, just want to know what it is. But we have the expectation that what we're going to find is a natural phenomenon, although one we haven't seen before, which is great.
Especially from Keith Bell, did you say this is not consistent with the May 2017 prediction from Boyajian et al.?
Did they predict May 2017? I didn't know that. Well,
nor did I.
If Tabby predicted that, then man, that's amazing. I didn't know about that prediction. Cool. Good going, Tabby. Email me the light from okay. Oh, people want access to the data I showed. Those are not my data. Matthew Nieverspa at Tennessee State University is the person to ask for the first one I put up, and you can ask me for the other one. I can clear with Tabby that we want to release that. I don't foresee any problem. I just want to be sure because they're not mine to give away. Any plans to continue the spectral analysis post-event? Yes, for sure. Like I said, what we want to see is change in the spectrum, because that lets us take out any instrumental features. And so a lot of instruments will be used for the first time on this star tonight and last night. And we will ask to use those instruments again at some point in the future when it re-brightens, so that we can do a proper difference. And
so there is indeed a sentence in Tabby's paper. A more robust prediction is that future dimming events should occur roughly every 750 days, with one in 2015 April and another in 2017 May.
Wow. Okay.
She hasn't mentioned what she predicted.
That's amazing. 750. Okay. Well, there you are. 750 days. Cool. So it's right on schedule. Maybe it'll be a really deep one. I'll have to, I guess, eat my words on those. That's amazing. Variable stars versus Tabby stars.
So I'm not sure that we talked at all about some of the historical monitoring that's been done, but with Automated Planet Finder, with the Breakthrough Listen program, we've actually taken 27 spectra since November of 2015.
Oh, 27 nights. I think it's even more than 27 spectra, but yeah.
So quite a lot of data, and a good fraction of that has been made public already at the Breakthrough Initiative's website. And I think the spectrum that we get tonight, we will release immediately. So maybe we'll certainly make that make that known as soon as we can. Cool.
I think we answered those. Do you want to grab some of these questions, Steve, for us?
Scanning through. I was just checking on Twitter. You can tweet us as well at Berkeley SETI. Or if you have questions, then you can ask in the chat window on the.
People have asked what makes this dimming so weird. Stars change brightness in a lot of ways for a lot of reasons, but this star looks ordinary. It's not a big giant. It's not a pulsating star. It's not. It doesn't have a disk of gas around it, and the dimming is way too deep to be due to planets. There are crazy dimming events that we see in stars sometimes if they have other stars orbiting them or binary stars orbiting them. But as far as we can tell, there's no evidence that anything orbits Tabby star, and we would have noticed by now if there were a star orbiting Tabby star with a period much shorter than a year or so.
If you briefly go over, I know, Jason, you've given a lot of thought to kind of different scenarios that might explain this and kind of the evidence for and against. That's a good idea. Just give us a quick rundown.
Right. So I think where it stands is that whatever is, okay, I think there are three overall ideas. One is essentially this giant comets hypothesis, that there's material that orbits the star, it's not very massive, and it's on a highly elliptical orbit. And so when it's close to the star, it heats up significantly, blocks the light, but then when we happen to point our telescopes at it, like Spitzer, and Spitzer can't get it, unfortunately, there's an issue there. The material is long gone, it's far away from the star, and so that's why we don't see the infrared excess. The second idea is that there is something between us and Tabby star that's causing something not orbiting Tabby star. So this would be material in the interstellar medium, the space between the stars, or even potentially in the outer reaches of our solar system. If that were a thing, we would expect that would happen to a lot of stars. It's hard to figure out why that would only happen to this one star out of all the stars that can be observed. But maybe it's a rare kind of cloud. And then the final idea is that it's something intrinsic to Tabby star itself, that there's nothing orbiting it or in between it, and it is just sort of spontaneously getting dimmer at these intervals, and slowly over time getting dimmer and dimmer. I haven't seen a really good physical mechanism for what would cause such a thing, and again, we're left with why Tabby star does it and no other stars do it. But at this point, I think all options are on the table. And so what would we expect to see in each of those scenarios? If it's material in the interstellar medium, then we expect to see the gases we associate with material in the interstellar medium. I said hydrogen, sodium, calcium, and we also expect to see a lot of dust. So we expect it to get much dimmer at ultraviolet and blue wavelengths than red. If it's comets and stuff around the star, we expect to see an increase in infrared radiation, and we expect to see similar gases and dust, but perhaps, if it's not too hot, also some ices, which you associate with comets. And then if it's the star itself, then we won't see any absorption features because there's nothing doing any absorbing. If a star gets dimmer, it has to be either because it got colder or smaller or some combination of those. If it gets colder, then we would expect the spectral features we see in its atmosphere to change. As it gets colder, the ionization and excitation levels of the atoms and ions in its atmosphere will change, and we'll see the spectrum, it'll change its spectral type. And if it's getting smaller, I guess in that case, it just will get dimmer and we won't see much else. But if it gets smaller, it should change its temperature. So we can tell temperature changes from that. And then if there's something opaque blocking it, like in cases where stars do have dense disks, those disks can just block parts of the stellar disk. In that case, the spectral features from the atmosphere that are rotationally broadened, it's a quickly spinning star. So we see that, for instance, it has hydrogen, but from the leading edge of the star, the hydrogen lines are shifted a little blue, and from the trailing, they're shifted a little red. From the Doppler shift, you block one of those hemispheres, you block that Doppler shifted light, and so the spectral lines that we see from the star will change their shape. And this has very broad lines, so that should be really obvious if that's happening. So those are all things that we're going to be looking for in these spectra. Those are our main targets. And those are the things that we are asking observers to focus on in their observations.
I'm afraid I have to run, but thank you all for joining us. Jason is going to stick around, I guess, for another...
Well, we'll go until we've figured out...
As long as there are good questions.
All
right. Well, everybody, stay tuned, and I think lots more excitement to come.
Jason, there's a question here from Ryan Dolly asking, can you address the long-term dimming detected by Schaefer in the Arbor plates and whether that or how that factors into what we're seeing today?
Right. so the long-term dimming is the second really strange thing Tabby Star does, in addition to the dips. Bradley Schaefer at Louisiana State University, interestingly, where Tabby is professor now, he went to the old Harvard plate archives. Harvard Observatory has been taking pictures of the sky for over 100 years on photographic plates. I don't think they do it any longer, but it went on for over 100 years. And these plates, it's kind of an art to be able to extract the brightness of stars from them, almost a lost art. But Bradley's been doing it for a long time and is very good at it. And he found that the star had dimmed over the last century by about 15%, 10 or 15%. And this was a bit controversial because, first of all, that's absurd. Stars don't do that. But also because the measurements are very difficult to make. And it requires an artistry that very few people possess to have high confidence in the measurements that you make. And there were changes of the instrument. Like I said, they used different telescopes and different plates over the years, and that can cause similar effects if you're not careful. And then Josh Simon and Ben Montet looked at the Kepler data, which is not intended to do that sort of long-term photometry. The Kepler telescope could detect sudden changes in brightness in stars, like the dips or like planetary transits, very well. But it was not designed to be able to tell the difference in brightness of a star across years or months. But they very cleverly used some calibration data that most people either didn't know about or had forgotten existed, and showed that you could use it to do long-term photometric monitoring. It was a very clever piece of work. And they showed that you can indeed extract good long-term photometry, and they checked many, many stars, dozens or hundreds of stars, and showed that, as expected, stars don't change their brightness over time, except one, and that was Tabby Star, which did dim by 4%, 3 or 4% over the 4-year mission, which was surprising to a lot of people. And it was a different rate and a different time than Bradley Schaefer found, but it's the same effect that he found. And so we've been monitoring it. Well, I say we, I haven't, but a lot of teams have been monitoring its brightness at a lot of wavelengths. There's a SWIFT campaign I am involved in, there's a Spitzer campaign, and a lot of observations, for instance, at the photometry I showed before at LCOGT and at Fairborn Observatory, and many others. The AAVSO has contributed lots and lots of photometry for this. And it's hard because you will need to wait several years before you're sure that you've seen it. But there do seem to be hints at what's approaching to be or just surpass formal statistical significance, that it continues to dim long term. But that's not what's happening now. What's happening now is a dip. It has dimmed as much in the last 3 days as it's probably dimmed in the last 3 years, and that's the difference.
Question from Off Planet: if you were to find anomalies pointing in the direction of the megastructure, what would be the next steps?
The next steps, whenever you think you found something you can only explain with aliens or something, is to try harder to explain it without aliens. We would start invoking models, I think, of rings of dusty material that's very cold, that are just blocking part of the star's light in some way. The only way that we're going to say that was it, we found them as aliens, is if we find, is if the Green Bank Observatory, the Allen Telescope Array, or one of these radio telescopes, or one of the optical or infrared SETI experiments, like on the Nicollet Lick Observatory with Shelley Wright's team, or the Automated Planet Finder here at Breakthrough Listen, detect clearly artificial signals of some kind. So radio waves, or laser beacons or something like that. You've got to see technology that can't possibly be natural. Otherwise, it'll just keep getting more mysterious, and we'll keep getting more frustrated that we can't find a really good model that explains all the observations.
I see Boyajian signed on to our live chat. Hi, Tabby.
Oh, great. Oh, hey, everyone. Hi, Tabby.
Yeah, Tabby's over in Louisiana, I guess, for the moment, Louisiana State.
Right, Baton Rouge.
And we're here in Berkeley, Berkeley SETI Research Center. Jason, you're heading back to Penn State this
I have a
evening.
red eye tonight back to Penn State. Yeah, so
And,
that'll be interesting.
You're going to have a busy weekend.
Yeah,
Tabby's going to have a
apparently.
busy weekend. We're going to have a busy weekend.
Indeed. Tabby, someone pointed out that you actually named May 2017 as a potential dip that might happen. And so your paper got it exactly right, which is awesome. The reason that the long-term dimming caused by the same mechanism. Oh, right. So the long-term dimming and the dips, they're pretty unrelated phenomena, except they both involve it getting dimmer. Or at least they were. Brian Metzger and Chen and Stone wrote a paper where they...
Ken Shen from UC Berkeley.
Ken Shen, yeah, Brian Metzger is also from UC Berkeley. They wrote a paper with sort of a grand unified model where the dimming of the star is intrinsic, but the dips are due to absorption. So in this model, something comes in a highly elliptical orbit, and it breaks up, and something like a planet or a brown dwarf, and most of the material falls into the star. This would have all happened long before Kepler started observing. Some of the material stayed in an elliptical orbit, and that's the comets causing the dimming, the dipping. But the long-term dimming is caused by the fact that when this thing falls into the star, it deposits all of that orbital kinetic energy that it had into the star, and then the star releases that energy as extra brightness. So essentially, the star swallows a planet or a brown dwarf. That makes it get brighter as it processes, its snack. But that's temporary, and eventually it goes back to its ordinary state. So the long-term dimming in this model is not due to any absorption. It's due to the star just slowly releasing all of that extra energy, and then losing that energy as it goes until it returns to normal. So a return to normal, not really a long-term dimming. But again, that unified model that explains both, it needs more quantitative work so that we can know what exactly we should see in the spectrum. If it's getting dimmer itself, like I said, the spectral type of the star should be slowly changing. But it also would predict that right now, or in the next few days or something, this material that's very close to the star should be hot, and so we should be seeing infrared excess, hopefully from LBT. That's next.
Derek and Keith saw that the Swift Space Telescope has Tabby Star in its schedule.
Yay! Thank you, Mike Siegel.
What instruments are on the telescope and what insights?
Yeah. So the Swift telescope is pretty amazing. We operated at Penn State. It observes gamma rays, X-rays, and it also has an ultraviolet optical telescope. And it was designed to solve the mystery of gamma ray bursts. So these very brief, intense bursts of gamma rays that for a long time were extremely mysterious. The telescope has a gamma ray detector with a huge field of view, and when it detects gamma rays, it stops what it's doing, and it immediately slews over, like in a matter of seconds, or a minute, or something like that. And there's this X-ray telescope to catch the X-rays from that burst, which can only last like a couple seconds or something. And then the UV and optical telescope can find the afterglow of the explosion that caused it. And it's hundreds of these or something. And it's amazing. And the nice thing about it is that you can retask it very quickly. Its schedule is not set months in advance. It's set like a day or two in advance. And so we have an ongoing program with a target of opportunity program, meaning we can trigger it. And so we put that in at 4 o'clock this morning or something like that. And so now we're getting regular observations with that. We've never seen any gamma rays from Tabby Star. We've never seen any X-rays from Tabby Star. But we do easily detect it at ultraviolet and optical wavelengths because it's a star and that's where it shines. And so we're going to be making brightness measurements of it. Swift was not designed to do precise stellar photometry. It is super good at what it does, but this is not what it does. And so I don't think the data we have so far show this dip. The error bars on the photometry are more like 1 or 2%, and it's only 2 or 3% down, so that's not statistically significant. But hopefully, if this is dust, it will be much dimmer at ultraviolet wavelengths than in the optical, where it's 3%, and we'll get a strong detection. And if it looks the same brightness, that means that it's not a very red dimming, which would mean that there's not dust involved, which is interesting.
So Tabby has actually answered in the live chat here about this prediction of a dip seen in May 2017. She said the prediction was a long shot. They cast a net of several hundred days. It was based on times Kepler observed the dip. I guess that's sort of a periodicity in the large dip.
That's right.
Does this suggest that there's some big structure
that's
coming around again? Or?
Right. So there were there was one really amazing deep dip halfway through the mission, and then right at the end of the mission, there was this incredible cluster of dips, including the deepest one we saw. And the deepest one we saw at the end there, and then that one really amazing one halfway through, were almost exactly 2 years apart. And so if you just take those two, and then you go 2 years, and then 2 years again, that puts you in March or February of this year. But I guess if you take that whole cluster at the end, and don't center on the deepest dip, but go a little later, then multiply that separation by 2, that puts you more like May. So, but I want to emphasize, there were a lot of other features too. It wasn't just those. Things happened not just there. And so I've actually been very skeptical that there's a 2-year periodicity, but the fact that we're getting one now perhaps confirms that. That would strongly suggest that it's something orbiting Tabby Star in like a 2-year orbit, which is hard to reconcile with the lack of infrared radiation. I guess maybe not if it's on an elliptical orbit. So maybe this is evidence that it's circumstellar to Tabby Star.
So somebody's asking if there is something coming around once every couple of years. Would that be in the habitable zone?
Not if it's on an elliptical orbit. In an elliptical orbit, it goes from really cold to really hot. A circular orbit at 2 years, I guess that's probably about right for the star, somewhere in there. It's on Swift. Okay. Any reasons that the long-term structure and dating caused by the same mechanism? Got that. If people are interested in more detail on the stuff I've said, a lot of it is on my blog, for instance. So Astro Wright is the name of the blog, and if you look for under research, there's all the different topics, and you can find my blog posts on this. You can watch the development of the story over the last couple of years as we've tried to solve the mystery. Do we have a list of who is observing the star? I'm trying to make a list. It keeps growing. I said at the top who I knew was on, so we'll recap again. Breakthrough Listen is hoping to get time on Green Bank tonight. We will definitely be observing with the automated planet finder at Lick Observatory. And Breakthrough's interest in that is that it is a kind of laser SETI search, but it will also get us a spectrum of the star, because that's what it does. Both observers on the twin Keck telescopes in Hawaii have told us that they'd be happy to grab spectra for us. Keck 1 will use blue high res, and Keck 2 will be a low resolution optical spectrum with ESI. The MMT observer tonight in Arizona will try to get us both a high res H alpha spectrum and a low resolution spectrum. I'm going to miss about Swift is observing. We can't use Spitzer because it can't point there. We're going to ask if we can use double spec on Palomar. The observers tonight, I think, are Yale observers, which is where Tabby was a postdoc when she discovered this. So I think she may know them. Of course, the Kickstarter funded Los Cumbres Observatory Global Telescope Network will be observing it as much as it can. We've increased the cadence on that. And so they'll be observing it. Fairborn Observatory, as always, will be observing it, and they were crucial to setting off this alert. And I know I'm missing other people that have promised, but it's kind of a busy day. LBT, 10 microns. Okay.
Sky and Telescope are asking the data that's now coming in public, and is there any way we can see it? Right. Derek O'Keefe pointed out the AAVSO data are public. Is there
AAVSO data are public. I should let Tabby know if she's still on that we've had requests for the LCOGT photometry. So if she could make that available with a link, I think that's public. And then I showed Matt Uterspaugh's data before, but again, that's not mine to give out, but I think he'd be happy to show it. So you can contact Matthew Niederspa at Tennessee State University for those data as well.
Brian quickly is wondering what's the observation plan if this lasts for a full month? Do we not getting very much sleep?
There's no sleep if this goes on for a month. I don't know. I mean, that's a great problem to have. I'll worry about that problem when I'm lucky enough to have it. I guess the observing plan is that things that take more time to do, to get organized, right? I mean, that'll actually give us time to respond to what we see. So if we see, for instance, that a new cloud of sodium has shown up, that's interesting, and then we'll want to monitor it, right? I mean, if it's one of these clusters that gets dimmer and brighter and dimmer and brighter, then we're going to want to see, does the optical dimming and brightening correspond to the sodium dimming and brightening, which would then indicate something about what's doing the broadband dimming versus the amount of sodium in the cloud that's doing it. If we see the spectral lines changing shape, you know, just seeing it change shape once is kind of an under-constrained model. But if as the star changes brightness, the line shapes change in a certain way, then you can maybe build a model of whatever is occulting the stellar disk. Yeah, it'll just make our summer much busier than we thought it was going to be. Oh yeah, someone was talking about high-speed photometry I see on the 2.1 meter. That would be fun. The Kepler, when Kepler observed it, the brightness changes were, I mean, it took measurements every 30 minutes, but there's no evidence in those data for any higher frequency changes. That is, when it changes brightness, it takes many hours to change brightness significantly. And then the dips would generally last somewhere between 1 and 7 days, depending on how deep they were. The deeper dips last longer. So we're hoping for a deep dip. And so in terms of monitoring, it's nice because it means that we saw something early this morning. Tonight we expect that it's still probably dim enough that observations are useful. And hopefully we'll get data from the Canary Islands tonight that will indicate that it's even deeper than it was this morning. And that'll mean we'll be getting some really great observations when the star finally rises in Arizona and in California and Hawaii tonight.
So this star has been called the most mysterious star.
The most mysterious. Well, yeah, I think it was Ross Anderson at the Atlantic who had the article that introduced the star to the world, the first public description of it, called the most mysterious star. Oh no, I'm sorry, it is not the first. Let me take this back and back up a second. When Tabby published the star, there was a press release about this star with the crazy comet. And so that was the first public announcement. But then Ross Anderson wrote the article about the SETI angle, and that's when things really blew up. And that was called the most mysterious star in the galaxy, the title of that article, which I've seen repeated many times now.
And do you think it still is? I mean, are there other?
Oh, I have my favorite weird mysteries in the universe. I have a blog post on my blog about Przybylski star and how it's even stranger in a lot of ways. But that's a problem that has bedeviled stellar astronomers for decades, and I think most of us have given up on it by now. So we've moved on to Tabby star, which is at least doing new stuff that we can study. Hopefully we won't just throw up our hands after 10 years of hard work, like we more or less had to do for Przybylski star, and not know what it is. Oh, I see Daryl LaCourse on. Daryl is one of the planet hunters that discovered Tabby star. So it's called Tabby star because she's the first author on the paper that her team, including all of the citizen scientists, wrote describing it. But of course, it's a whole team effort. A lot of people put a lot of work into it. Sometimes people, ask why we weren't doing all of this during the Kepler mission when it was getting dimmer and acting so strangely. Like, why weren't we pointing telescopes at it then? And the reason is that Kepler had a lot of strange stars doing weird things, and some of it was bad data, Some of it was, you know, weird triple or quadruple star systems. There are a lot of strange, or young stars, well, I guess there weren't any young stars with disks in the Kepler-Planck field, but a lot of weird variables. And most of them turned out to have complicated but ultimately mundane explanations. And it just takes a long time to figure out what those are. And it took Tabby's team, I think, about 2 years of hard work and follow-up and just banging their heads against this to finally decide that it was a mystery that wasn't going to get solved by the time they had to write the paper. And so it was only after all that hard work to show there was no disk, there was no infrared excess, it's an ordinary F star, it does not have an orbital companion, you know, it is not bad data. Only after all of those things had been ruled out that it became mysterious. And so now we're lucky enough that it's dipping again, which is really exciting.
Ross K was asking about the percent depth of the deepest one seen previously, 22%.
Yeah, I think it was 15 and 22 were the two deepest before. And the others were all, well, I mean, there's a whole range of them. The deeper the dip, the rarer the dip. But typically a few percent was kind of a typical dip.
And there's nothing to rule out that this one is heading in that direction.
No, this one is as steep. I'm pretty sure this is as steep as we ever saw it change brightness in Kepler, just from memory of the Kepler light curves. So that's promising. I mean, this thing could go down and, you know, maybe in 3 days it'll still be dropping. That would be pretty amazing. Or maybe we'll get the Canary Islands photometry in 6 hours or whenever it comes, and it'll be on its way back up, and it'll turn out to have been a very short dip.
And the smaller dips that have been seen, you know, how many more observations do you need to sort of tell the difference between one of these smaller irregular dips and one of the big ones? That'll be in a day or two that you'll be able to say for sure.
Well, I mean, the deep ones last longer,
right? And
they go deeper. And so, you know, in the photometry I was showing before, do you want to put the LCOGT up before? Because I know that's been shared widely.
That's this one here.
Yeah. So here you can see the photometry in the last 2 nights. It got dim and then much dimmer. I mean, if that keeps going, then the star could end up 10% dimmer in just a few nights. And on Wednesday, we'll be like, this is amazing. On the other hand, it could go right back up. Some of the dips were very V-shaped in the Kepler data. That is, it's not like a planetary transit where it gets dimmer and then it stays dim for a while and then returns. Usually, the dips had V-shapes. And so they would sort of reverse without warning and then go back up to where they were. So that'll create some drama. That to the degree that we can describe the shapes, yeah, they turn around. They turn on a dime. Yeah, we can go back.
Okay, we've just got a few minutes left here before the top of the hour. I know you're going to be scrambling, Jason, to deal with all of the other.
Yeah, I've got a blue side setup, which I've never done before, and coordinate a bunch of stuff. I still have to put in my ATT trigger. I have some time on that, though. I have to do them in order of longitude, because I have more time for the Keck one before I get on my flight tonight.
Any last questions? ALMA. Would ALMA be useful right now?
Oh my gosh, if someone could figure out how to get ALMA to planet this thing. ALMA's in the southern hemisphere, and Tabby Star's in the northern hemisphere. But technically, I mean, literally it does rise. If you're at the ALMA site, Tabby Star will go above the horizon. But pointing a giant radio telescope array that, you know, still isn't fully operational in all of the corner cases, that low at the horizon, I think, is an operational mode that no one wants to shake down right now. So we've talked about how maybe to just take the data and worry about how to reduce it later. But anyway, if anyone can get ALMA pointed at that thing, that would be fantastic. We'd really love whatever ALMA can offer. ALMA's a millimeter radio telescope, sub-millimeter telescope at a common desert, and it's an amazing instrument, and I would love to be able to plant it at Tabby Star. But I think it's such a popular instrument because it's so powerful that trying something crazy like pointing it at the horizon to catch this star for a few minutes as it comes above is just a little too high risk for what, compared to all the other amazing science it's doing. We keep trying.
Tony Jepson is wondering if the nearby M dwarf is somehow interacting with the main star.
I wonder that too. Yeah. So Tabby's team discovered that there's a companion star, and it's presumably a small MS star in orbit around Tabby's star. But if it's an orbit, it's in a very long, wide orbit. We don't see it move in its orbit. It would take, I don't know, millennia to go around or something. And when we first saw that, we're like, yes, that must help explain things. Right now we'll figure it out. But in the end, I think it turned into a red herring. But who knows? Maybe it'll end up being part of the solution. Maybe it explains why all this material is on an eccentric orbit.
Okay, we're coming up to the top of the hour. In the absence of any other questions, I'd just like to thank everyone for joining us here today at Berkeley SETI Research Center here at the University of California, Berkeley. I'd like to thank Professor Jason Wright for giving us an hour of his time on this really busy day. Jason mentioned you can go check out his blog. You can follow him on Twitter, astro_Wright. You can follow Berkeley SETI Research Center on Facebook, Twitter, Instagram, and YouTube at Berkeley SETI. You're obviously here on YouTube already, so you know that we're out here. And visit us at seti.berkeley.edu. You can also visit the Breakthrough Initiatives Breakthrough Lesson on the web and on Facebook and Twitter as well. We'll be updating, I guess, over the next few days, kind of what's going on, and pretty exciting times. Yeah. Pretty hectic. It is, and I'm supposed to be reading 3 dissertations right now for defense coming up in the next 2 weeks, so it's going to be a busy couple weeks. Okay, well, thanks everybody for joining us, and stay tuned.